Today we are taking you underwater with skin diving, into the sky with hand gliders, and then back down to earth to talk about gymnastics. We have all seen pictures of shipwrecks lying on the ocean floor. They make an impressive sight, those colossal, gutted carcasses. But no more so than the sight of teams of divers moving about the wreckage as freely as curious fish. For years, the diving suit was used, but this system has a major disadvantage. Divers, attached to a long tube that supply them with oxygen, are limited in their movements. Diving suits are still used, but most divers now prefer the aqualung, which was developed some 40 years ago by the French sea captain, Jacques Cousteau. For a long time, the underwater world was virtually inaccessible to man. But in recent years, the doors of that universe have opened to us. Thanks to self-contained underwater breathing apparatus, we can now navigate freely under the water to carry out any number of tasks, from rescue operations to simply satisfying our unquenchable thirst for knowledge. However, entering a water environment does require some adaptation. For one thing, there's no air. Skin divers have to carry their own tank of compressed air in order to breathe. The device that draws from the tank and gives them every breath of air they need is called a purge valve. The purge valve lowers the pressure of the compressed air, which is very high, down to the ambient pressure level. The diver then expels the tainted air into the water, where it forms a rosary of bubbles. With this equipment, divers may stay underwater for relatively long periods. However, as depth increases, the period of time decreases. The marine environment poses other obstacles that could endanger their lives. Such problems are caused by the effects of water pressure on the human body. Underwater, just like above water, objects are constantly subjected to pressure, atmospheric pressure. That pressure comes from the weight of the immense mass of air in the atmosphere. That mass of air exerts dozens of tons of weight on our bodies. But we are perfectly adjusted to the pressure and do not feel it. But as a diver goes deeper into the water, the pressure he is subjected to quickly increases. At a depth of 12 meters, a diver is subjected to twice the atmospheric pressure. At 20 meters, it's 3 times higher, and so on. This rapid increase of pressure with the water depth is potentially dangerous for the human body. One of its effects can be compared to carbon dioxide dissolved in a fizzy drink. Under the effect of pressure, the carbon dioxide introduced in the drink dissolves. That is, it blends completely into the liquid. Something similar occurs when the diver is subjected to an increasing water pressure. Under the effect of the pressure, part of the air the diver breathes dissolves in his body tissues and liquids. Since 78% of air is nitrogen and 21% oxygen, most of the gas that dissolves in his body is nitrogen. This phenomenon does not affect the diver during his descent. However, it can be dangerous when he ascends. Indeed, when he comes back up, the pressure decreases and the nitrogen tends to leave the diver's tissues and become gaseous again. If the diver resurfaces too quickly, or if too much nitrogen has built up in his body, it will form bubbles, exactly like what happens in a soft drink bottle when the cap's taken off too quickly. The nitrogen bubbles can seriously threaten the diver's life. As the diver ascends, the bubbles increase in volume. This phenomenon, whereby the volume of a gas increases as the pressure decreases, is explained by a law of physics. The bubbles can get into the joints, blocking the circulation and causing painful symptoms known as the bends. If the bubbles reach the vital organs, like the lungs, brain, or spinal cord, they can cause asphyxia, paralysis, or death. When a skin diver shows symptoms of the bends, he must be rushed to a decompression chamber, also called a hyperbaric chamber. In this chamber, the diver is given oxygen, and the pressure is increased up to 6 times the normal atmospheric pressure. The increased pressure makes the bubbles of nitrogen decrease in size and dissolve back into the diver's bloodstream and tissues. The symptoms can vanish in a matter of minutes. The pressure is then lowered very gradually over a period that can last several hours. This enables the dissolved nitrogen to be expelled from the lungs without making bubbles. Fortunately, it is possible to prevent the bends. Using special tables, divers can carefully plan the duration and depth of their dives. By doing this, they can keep the nitrogen building up in their body from exceeding the critical level, beyond which dangerous gaseous bubbles may form. If necessary, they can also go through several levels of decompression, that is, make stops during their ascent. The various stops help to eliminate any excess dissolved gas. When divers are careful to follow these precautions, scuba diving is even less dangerous than driving a car. Thanks to skin diving equipment, man can be like the fish. And thanks to hand gliders, he's able to imitate the birds. The hand glider is one of the more modern versions of an invention as old as the hills, the sail. Since the 60s, hand gliding has become very popular. The principle is really very simple. You run about 20 to 30 meters, preferably down a slope. You pick up speed until you can lean against the air and lift off the ground. Then all you have to do is make the most of the ascending air currents to remain airborne as long as possible. The air around us is more than a mere gaseous mixture, vital for our survival. For many of us, that invisible gas is the source of a whole range of thrills and chills. It is thanks to the air and its movements that sailboats crisscross the oceans and gliders and hand gliders seem to defy the laws of gravity. The popularity of these sports is due in part to the progress made in building techniques and the new materials used. But it's also due to a better knowledge of the physical laws governing the movement of air masses. Although sailboats have been around for ages, it was only recently that the principle of their propulsion became known. A sail is subjected to 2 different forces. The first of these forces is the pressure of the air exerted behind the sail. That pressure is the result of the frantic movement of the molecules of air colliding and bouncing off each other, a little like billiard balls. Since the sail exerts a resistance to the wind, the air molecules tend to concentrate behind it. In this area, the air molecules are closer together than at the front of the sail, so they collide more often. This heightened agitation of the air molecules causes the sail to swell and gives it a push forward. However, contrary to what we might think, the push is not the most important of the forces that affect the sail. Indeed, a sailboat's movement is often the result of a principle of physics called Bernoulli's principle, after the Swiss mathematician who formulated it 250 years ago. Bernoulli's principle states that the narrower the channel through which a moving gas or liquid flows, the greater its velocity, but the less pressure it exerts. Bernoulli's principle only applies when the sail swells and its outer surface is curved. When this occurs, the flow of air over the outer surface of the sail has a narrower pathway than across the inside surface. The velocity of the air flowing over the outer side increases, hence the pressure it exerts decreases. A veritable vacuum is created in front of the sail. Laboratory tests have shown that this suction effect is the main force that propels sailboats. Bernoulli's principle enables modern sailboats to achieve feats that at first glance seem impossible. So, some sailboats can go twice as fast as the wind pushing them. Moreover, although sailboats cannot head directly into the wind, they can be made to do so to a certain degree. The lateral force the wind exerts on the sail is offset by an opposite force exerted by the water on the boat's keel. Instead of being pushed over on its side, the sailboat is thrust forward. By tacking, that is zigzagging in the opposite direction of the wind, the sailboat can manage a heading exactly opposite to the direction of the wind. It's also due to Bernoulli's principle that gliders and hand gliders can effectively fight the laws of gravity for periods of up to several hours. That's because their wings are curved, a little like a ballooning sail. The streams of air encountering the upper part of the wings suddenly have a smaller space to flow. The flow of air molecules speeds up, so the pressure they exert decreases. That decrease in pressure creates drag that sucks the wings upward. The greater the velocity of the air molecules over the wing surface, the greater the impact of Bernoulli's principle. For this reason, it is important that the pilots of gliders and hand gliders take off at the highest initial speed possible. They do this by launching their craft from a tow plane or jumping off an elevated point. While these craft follow an oblique trajectory that sooner or later will bring them back down to Earth, their pilots can sometimes keep them flying for hours due to the effect of the heat on the molecules of air. In some regions, the rays of sunlight heat the ground more in a certain area. That heat is transmitted to the air molecules, increasing their collisions. The molecules of air move away from each other and the air, less dense, rises. These vertical movements of air, called updrafts, enable hang gliders and gliders to gain altitude and to stay in flight for hours. Am I giving you a rough time? After seasickness, now I'm giving you air sickness? Well, let's get back down to Earth. Here, the sophisticated, cutting-edge equipment we're going to talk about is the human body. Whether it's a triple backward somersault or just a few tango steps, all our motor skills depend on our ability to position our body in space and to maintain our balance. Since the very beginning, gymnastics have never ceased to be a source of amazement and wonder. Over the years, gymnasts have improved their performances constantly to the point where they are now able to execute movements once deemed impossible. The training of these exceptional athletes requires a rigorous selection process and sustained coaching. During their training, begun at the earliest possible age, the athletes learn how to develop their physical capabilities, such as flexibility, strength, endurance, and power. But like most activities, the practice of gymnastics depends on two other essential skills. These skills, called motor skills, are the capacity to position one's body in space and to maintain one's balance. The capacity to position one's body in space is linked to a faculty we all have and scientists call proprioception. Owing to proprioception, a veritable sixth sense, we know at all times what our body's position and movements are in the three dimensions of space, and without the use of eyesight. Like all our other senses, proprioception comes from all sorts of information that is gathered by minuscule organs called receptors. So called because they receive information about the external environment. Receptors are located in various parts of the body. Some receptors are found in our muscles, called neuromuscular spindles. They are elongated and surrounded by a spiraled nerve fiber. Neuromuscular spindles provide information on the degree of tension in our muscles. Every time a muscle contracts, the spindles send a signal to the brain. The same occurs when the muscle resumes its original posture. Thanks to the neuromuscular spindles, the gymnast's brain is constantly informed as to the degree of tension and stretch of all the muscles in her body. The joints also have their own specialized receptors. These receptors go into action when a joint opens or closes. The information sent to the brain tells the gymnast at what angle of flexion her various limbs are, and hence their position in relationship to each other. Proprioception is also based upon a tiny organ nestled in the inner ear, the vestibular system. The vestibular system consists of 3 semicircular canals filled with fluid and having tufts of sensitive hair cells at their base. 2 small vesicles are attached to the canals, the utricle and the saccule, which also have hair cells. The vestibular system serves to assess the head and torso's posture and movements in relationship to the vertical axis. When the gymnast bends her head or torso, the vestibular system fluid and hair cells at first remain motionless due to their inertia. Then they go into motion and resume their initial position. By moving, the hair cells transmit nerve impulses to the brain. All this information enables the brain to draw a veritable mental diagram of the body and to control its movements with precision. In addition to enabling the gymnast to position her body in space, proprioception ensures another vital skill, maintaining balance. For there to be balance, the gravity exerted on the body must be counterbalanced by an equal and opposite force. The human body is an unstable structure. Left to itself, it would not be able to remain upright and offset gravity. To ensure balance, the signals from the muscles, joints, and vestibular system are sent along to the cerebellum, located behind the brain. The cerebellum is essential for the synchronization of activity in the body's numerous muscles, enabling them to counteract gravity and maintain balance. It is by educating their cerebellums that babies can begin to stand up. In their training, gymnasts take that initial step much further and learn how to keep their balance when they are spinning in an upside-down position, or even in the air. An important part of a gymnast's training consists of ever improving the ability to position the body in space and to maintain balance through a variety of exercises repeated over and over again. Coaches and scientists still do not know why these faculties develop more quickly in some people than in others. The one thing we know for sure is that these gifted children can, with hard work, become great gymnasts. When I'm windsurfing, I forget about all the neuromuscular junctions in my body and molecular physics, thank heavens. But there is always something to be learned. Even lying on a beach, I could find out about the combined action of vitamin C and the sun on my melanocytes. You know, there are times when I could really use a long holiday.